Welcome to this first video, and actually the first video in the playlist on differential equations. I know I touched on this before when we did harmonic motion, and I think I might have touched on it in other subjects. But now, because of your request, we'll do a whole playlist on this, and that's, I think, a fairly useful thing because differential equations is something that shows up in a whole set of different fields. I've been requested by someone who's starting an economics PhD program to do this. I've been requested by some people who are going into physics, some people who are going into engineering. So it's widely applicable area of study. So let's just get started before I keep going off on useless stuff. So the differential equation. So the first question is, what is a differential equation? You know what an equation is. What is a differential equation? Well, a differential equation is an equation that involves an unknown function and its derivative. So what do I mean by that? Well, let's say that I said that y prime plus y is equal to x plus 3. Here the unknown function is y. We could have written it as y of x, or we could have written this as dy dx, the derivative of y with respect to x, plus this unknown function y is equal to x plus 3. We also could have written f prime of x plus f of x is equal to x plus 3. All of these would have been valid ways of writing this exact same differential equation. And what's interesting here, and how this is a departure from what we've learned before about just regular equations. Let me write down a regular equation just to remind you what they look like. So a regular equation, if we had one variable, would look something like this. I don't know, x squared plus, I don't know, the cosine of x is equal to the square root of x. I just made that up. Here the solution is a number, or sometimes it's a set of numbers. Sometimes there's more than one, right? If you have a polynomial, you could have more than one values of x that satisfy this equation. Here, for a differential equation, the solution is a function. Our goal is to figure out what function of x, and here I wrote f of x explicitly, but what function of x explicitly satisfies this relationship or this equation. So let me show you what I mean by that. And I have my differential equations book from college, so I'm going to use that as we go. So let's say that I'm just writing down. Let's see, they have this as a differential equation. Y, and I'm not going to show you necessarily how to solve them just yet because we have to learn some tricks first. But I think a good place to start is just so you understand what a differential equation is, and so you don't get confused with the traditional equation. So they have this differential. This y prime prime. So the second derivative of y with respect to x plus 2 times the first derivative of y with respect to x minus 3y is equal to 0. And they give us the solutions here. And what they want us to do is show that these are solutions. And I think this is a good place to just at least understand what a differential equation is and what its solution means. So they say y1 of x is equal to e to the minus 3x. So they claim that this is a solution of this differential equation. So let me show to you that this is. Well, if this is y1, what's y? Well, I don't have to. Well, let me just write y1. What's y1 prime? What's the derivative of this? Well, just do the chain rule. The derivative of the whole function with respect to this part of it, is just e to the minus 3x. And then you take the derivative of the inside. So that's just the derivative of the outside, e to the minus 3x. And the derivative of the inside is minus 3. Right? And then the second derivative of y1 is equal to, we'll just take the derivative of this, and that's just equal to plus 9, right? Minus 3 times minus 3, e to the minus 3x. Now let's verify that if we substitute y1 and its derivatives back into this differential equations, that it holds true. So y prime prime, that's this. So we get 9 e to the minus 3x plus 2y prime plus 2 times y prime. Well, this is y prime. So 2 times minus 3 e to the minus 3x plus, minus 3 times y. Well, y is this. So minus 3 times e to the minus 3x. Well, what does that equal? That we get 9e to the minus 3x minus 6e to the minus 3x minus 3e to the minus 3x. Well, what does that equal? We have 9 of something minus 6 of something minus 3 of something. So that just equals 0. It doesn't matter if 0 of whatever. So that equals 0. So we verified that for this function, for y1 is equal to e to the minus 3x, it satisfies this differential equation. Now there's something interesting here, and you've kind of touched on this with regular equations, is that this might not be the only solution. In fact, we'll learn in maybe a video or two that often the solution isn't just a function, it could be a class of functions where usually they're all kind of the same function, but you have a difference of constants. But I'll show you that in a second. But here they actually show us that there's another solution, that this will actually work with, we could try the equation y2 of x is equal to, well, just simple e to the x. And we could verify that, right? What's the first and second derivatives of e to the x? Well, they're just e to the x. So the second derivative of y2 is just e to the x plus 2 times the first derivative is what? Well, the first derivative of e to the x is still e to the x, 2e to the x, minus 3 times the function, minus 3e to the x. Well, 1 plus 2 minus 3, well, that equals 0 again. So this was also a solution to this differential equation. Now, before we go on, in the next one, I'll show you some fairly straightforward differential equations to solve. I think it's a good time now that you hopefully have a grasp of what a differential equation is and what its solution is. That its solution isn't a number. Its solution is a function or a set of functions or a class of functions. It's a good time to just go over a little bit of terminology. So there's two big classifications. Well, actually, there's a first big one: ordinary and partial differential equations. I think you might already guess what that means. An ordinary differential equation is what I wrote down. It's one variable with respect to another variable, or one function with respect to, say, x and its derivatives. Partial differential equations we'll get into later. That's more complicated. That's when a function can be a function of more than one variable, and it has, you can have the derivative with respect to x and y and z. We won't worry about that right now. If your functions and their derivatives are a function of only one variable, then we're dealing with an ordinary differential equation. And that's what this playlist will deal with: ordinary differential equations. Now, within ordinary differential equations, there's two ways of classifying, and they kind of overlap. You have your order. So what is the order of my differential equation? And then you have this notion of whether it is linear or nonlinear. And I think the best way to figure this out is just to write down examples. So this differential, let me write down one. I'm getting this from my college differential equations book. X squared times the second derivative of y with respect to x plus x times the first derivative of y with respect to x plus 2y is equal to sine of x. So the first question is what is the order? Well, all the order is the highest derivative that exists in your equation, the highest derivative of the function under question, right? The solution of this is going to be a y that satisfies a y of x that satisfies this equation. And the order is the highest derivative of that function. Well, the highest derivative here is the second derivative. So this has order 2. Order 2. Or you could call this a second order ordinary differential equations. Now, the second thing we have to figure out, is this linear or is this a nonlinear differential equation? So a differential equation is linear if all of the functions and its derivatives are essentially, well, for lack of a better word, linear. What do I mean by that? I mean you don't have a y squared, or you don't have a dy over dx squared, or you don't have a y times the second derivative of y. So this example I just wrote here, this is a second order linear equation because you have the second derivative, the first derivative, and y, but they're not multiplied by the function or the derivatives. Now, if this equation were, if I rewrote it as x squared d the second derivative of y with respect to x squared is equal to sine of x. And let's say I were to square this. Now all of a sudden I have a nonlinear differential equation. This is nonlinear. This is linear. Because I multiplied the second derivative of y with respect, I multiplied it times itself. Another example of a nonlinear equation is if I wrote y times the second derivative of y with respect to x is equal to sine of x. This is also nonlinear because I multiplied the function times its second derivative. Notice here I did multiply stuff times the second derivative, but it was the independent variable x that I multiplied. But anyway, I've run out of time, and hopefully that gives you a good, at least, survey of what a differential equation is. In the next video, we'll start actually solving them. See you soon.